Alright, so today I'm going to be explaining this important paper with the title Equivariant Neural Diffusion for Molecule Generation. This NeurIPS paper in 2024. So we introduce equivariant neural diffusion, a novel diffusion model for molecule generation in 3D that is equivariant to Euclidean transformations. Compared to current state of the art is 2024. Compared to current state of the art equivariant diffusion models, the key innovation lies in its learnable forward process. Because most of the diffusion processes, they don't learn the forward, they just learn the denoiser, which is in the backward. But this paper, it says that rather than pre-specify a forward process, is parameterized through a time and data dependent transformation that is equivariant to rigid transformation. So through a series of experiments, we demonstrate the competitive performance. So their model is called END, equivariant neural diffusion. So because we model molecule in 3 dimensions, so in E3, we consider 3-dimensional Euclidean space that represents molecules. So each atomistic system can be described by R and H, where R is this form a collection of vectors in 3D. So the coordinates of atoms are R, and H are the associated scalar features, for example, atom type. When dealing with molecules, we are particularly interested in E3, which is the Euclidean group in 3 dimensions, generated by translations, rotations, and reflections, E3. Each group element in E3 can be represented as a combination of a translation vector and an orthogonal vector, orthogonal matrix R encoding rotation or reflection. So while scalar features H remain invariant, coordinates because atom type is the same thing, but you can rotate your molecule, you can do reflection. So a function is said to be equivariant of a group G to the action of the group G, or we call it G equivariant if you first do that equivariant transformation and then apply the group transformation, is the same as first do the group transformation and then apply the transformation. And then so it is E3 equivariant if this holds. A conditional distribution is equivariant to rotations and reflections, while a distribution is said to be invariant when P of X is P of Rx. So diffusion models are the equivariant diffusion model is a particular instance of a diffusion model. So the learned marginal probability is made invariant to the action of translation. It means that probability of, for example, nodes and edges of a molecule, if you just rotate it and then check the probability, it's the same thing. So the forward process, you can perturb samples from data distribution, over time through noise injection. So it results a trajectory of latent conditional on X. The conditional distribution for Z given X can be described by an initial distribution. So EDM implements the variance preserving STE. When this your drift is as simple as this, and these are special cases. For example, here is just half of beta. Of course, if you have a fixed schedule beta, then F is very simple and can be reconstructed like this. So this alpha is just e to the, so everything is explicit. Your mean and your variance is explicit because the form that you have chosen for your drift is simple, okay? And then we call the reverse. For the reverse time STE, unfortunately, you need to learn this. You need to learn the following scores. The reason that we multiply because it's not only for positional but also for the atom types as well, the features as well as the positions. So that's why we have two things. And because Z is composed of Z of R for the positions of them and Z of H for the features of that. So that's why the score of that is log of Z when the gradient in the ZR direction and also the gradient in the ZH direction of log of Q of Z. And Q of Z, but now you are differentiating with respect to position, but here we're differentiating with respect to your features. So with the learned score, after you learn this score, a sample can be obtained. So we can simulate the reverse by these learned scores, where the true score has been replaced by the approximation. Okay. So in EDM, the approximate score is parameterized through an equivariant function. This is realized through specific parameterization. So our score, we parameterize it like this. Because it should be a function of Z, so now you see it's a function of Z. All elements are a function of Z. So where the data point, x hat, is implemented by an equivariant. This x hat is coming from an equivariant neural network. This is a data point predictor. So the data point predictor is just optimize this denoising score matching. I have a playlist for denoising score matching. So I reviewed this paper, Vincent, in 2011. So neural flow diffusion models are based on the observation that latent variables are conventionally inferred through a pre-specified transformation, as implied by the chosen type of STE and noise schedule. This potential limits the flexibility of the latent space and makes the learning of the reverse process more challenging. So in contrast, it has pros and cons. If you say that I want to make it fixed, I don't want to learn the forward process, no learning, the pros is that you can calculate the score very easily because you want to learn it, so it's simple to analytically obtain it. But the cons is that if it is simple, you are restricting the class of forward, the trajectories in the forward process. You're restricting that, so the denoiser has a hard time to find, to estimate that. So there is a pros and cons. But they decided to take the learning of the forward. They try to, of course, they missed the explicit solution of the score, which is easy to obtain if your forward is simple. But let's see what happens. The latent variable z are obtained by transforming noise samples, condition and data point, and time step. So if f is differentiable with respect to epsilon and t and invertible with respect to epsilon, then for fixed x and epsilon, samples from q can be obtained by solving this conditional ordinary differential equation. Then, so given access to equation here, this is z here, this latent here, so while f and q define a conditional marginal distribution, we need a distribution over trajectories. So given access to that, the score function and the conditional SD share the same marginal distribution. So you see the score here, and the score function, as you see, you can write it very easily like this. Now you know what epsilon is. Epsilon is here, and J, the Jacobian, is here. A conditional reverse SD that starts from Z runs backward and reverses the SD. So for the reverse, let's see what happens. Now it is replaced by this one. So this is the score, but the important thing is here. How do you learn this score? Then, as X is known when generating samples, we can write this equation 3 with prediction of X instead. So X hat here is a function that predicts the data point. Given the latent, you can predict the data point. Provided that a reconstruction distribution and prior are defined, this fully specifies the reverse process. So the forward reverse process and the reverse process can be optimized by just matching the drift term of the true. This is the true and the approximate conditional reverse SD. But both of them are a function of Z, and expectation is over U as well as Q. So this is equivalent just to KL divergence between the posterior distribution. If you discretize 3 and 4, then this loss is very much like the KL divergence of that. But because this is the continuous one, so we are matching the SDEs. We now introduce equivariant version of that, which is called END, as I said, that generalizes equivariant diffusion model by defining a forward process through a learnable transformation. Our approach is a synthesis on NFDM and leverages ideas of EDM by providing an equivariant learnable transformation. We show that it is possible to obtain a generative model with desired properties. So the key innovation is in the forward process, which is also leveraged in the reverse process. The forward is defined as a learnable So as you see, it's a learnable time and data dependent, both related to time and data X as well. So the latent Z, it is defined such that the latent Z transforms covariantly with the injected noise. So we then define X hat as another learnable equivariant function such that the predicted data point transforms covariantly. You see, if I first transform and then apply Z, the reflection of that, and then get the X hat, is the same as first do X hat, then give it to the matrix R. So this is, we have done it covariantly. So we choose a noise and prior distribution to be invariant to the considered symmetry group. So P of Z1 an invariant distribution and F an equivariant function. So this can be shown by demonstrating the reverse STE is equivariant. We start by noting that the reverse STE is given by this. So your drift F hat is equivariant now because of this relation. You've got a equivariant drift. As a drift is expressed as a sum of two terms, we inspect each of them separately. So the first term of the drift is this one, which is first F is equivariant, because if it is equivariant, then its time derivative is also equivariant. You can check this appendix. So in addition to an invariant prior, an equivariant X hat ensure the equivariance of the reverse process. So we introduce a simple parametrization of f of phi. So U is a structured, U here is a structured block diagonal matrix. So each block is 3 by 3, ensuring a cheap calculation of inverse information, and it's Jacobian. This is equivalent to diagonal parametrization in case of scalar features. So because of U, they have done a very smart and simple parametrization. So our parametrization leads to conditional marginal, that is conditional Gaussian with block diagonal. But the mean and covariance are now data and time dependent. So both mu and this U must be equivariant functions whose output transform covariantly with X in order to ensure the desired equivariance of F. So we can then readily check that Q is also equivariant. So it can be advantageous to parameterize the transformation such that prior and reconstruction losses need not be computed. To do so, we design F such that the conditional distribution evolves from a low variance Gaussian centered around the data to an uninformative prior distribution. So we implement F by a neural network. So this is for training end. You just match the drift, and then this is the stochastic sampling from end. Once you have learned f